Welcome back to the EXD. By the end of today's episode, you will understand how mRoPE, a cutting-edge positional embedding technique, works. You will be able to explain the motivation for using rotational embeddings and describe how it's implemented step by step in the Qwen 3.6 model that we've been taking apart in this series. In this episode, we'll also start doing some linear algebra, but don't worry, we're going to keep it very simple and mainly descriptive. No proofs, at least not yet. My name is Ram, and this is an open learning log that I call the EXD. To start at the beginning, check out episode 1. I'll link it in the description below. Okay, let's start. Before we get into mRoPE, a quick note about the way of the EXD. As I've mentioned in previous episodes, in the EXD we like to learn by working things apart and looking at the pieces and trying to figure out how they work. This is because I've always struggled with building up from theory bit by bit until we reach like concrete implementations. I'm kind of the person who likes to take a working engine and, grab a wrench and start removing panels and sort of taking it apart slowly, bit by bit, to understand how it works. And that's what we're going to try with models in this series. So that's just a quick note on how we do things in the EXD. So if you're going to learn about mRoPE today, we're going to learn using the actual embedding in Qwen 3.6, the actual embedding technique. Let's look at this. So let's look at this engine. In the last few episodes, this is what the engine looks like. These are the big chunky pieces. So, these are pistons, this is a carburetor, etc., etc. So in the last 3 episodes, we have looked at these first 3 bits in detail. We have taken them apart and even implemented some of these bits. And today we're going to look at this piece, the positional embedding piece, which is the last step before we enter the transformer. So as usual, let's switch to my Hugging Face space. This is my space on Hugging Face. You can check out all my episodes here and all the articles. And today's episode is mRoPE, multi-resolution rotary position embedding. And we're going to look at this in Qwen 3.6, 35B, A3B. So this is the mixture of experts model. Okay, let's get right into it. A quick refresher and also a quick note. If you haven't seen the embeddings episode yet, I suggest you go back 3 episodes and take a look. I'll also link them below. That'll be a better starting point for you. But let's do a quick recap. So we already know that a token embedding is a vector, which points to a point in a 2048 dimensional space of real numbers. So the embedding for cat, then happens to be cat with a space before it, if you remember. And the embedding for cat is the same vector regardless of where it appears in the sentence. So, which makes sense. You kind of want the representation of cat to always mean cat, but it creates a problem. So if you look at this sentence, the dog bit the man and the man bit the dog, all the vectors individually are the same, but their position in the embedding completely changes the meaning. Just because dog appears here and man appears here, one becomes the biter and the other the bitee. So position matters as well. So we already know how these embeddings for the individual things for individual tokens are created today, and we did discuss how positional embedding works and how you add a little bit of more information to encode the position of the token in the sequence, in the input sequence. And one of those, and the technique that Qwen uses is mRoPE. Okay? So we talked about this in a previous episode. This is a little bit of a recap, but essentially there is a naive approach where what you could do is just take the existing vector. Let's say this represents dog, and just add a tiny little vector to it, so that you get a new vector which represents dog plus the position of dog in the sentence. Okay? But there is a problem with this naive approach, which is that it's encoding an absolute position. Here, I is the index of the token in the sentence. So, for example, if you look at this, dog here has the index. If this is 0, then dog has the index 1 in this sentence. But in this sentence, dog has the index 0, 1, 2, 3, 4. Right? So, I is equal to 1 here, and I is equal to 4 here. So the problem is, if you look at this sentence, and this is a toy example just to underline the problem. If I just shift it by this entire sequence by 7 empty spaces, the meaning of the sentence hasn't changed, but the position has completely changed, and therefore the new vector, the positionally encoded vector, is completely different. But that's actually not what we want. So it turns out what we really want is the positions of tokens relative to each other. That's what we want to encode. We don't care about absolute position, simply because they can appear in different places in a input sequence. Either it could be empty spaces before them or some other text. So the point is, we just want to sort of encode this relationship between them without being stuck with an absolute encoding. So what we want to capture is relative position. Okay? So let's just make sure we understand that clearly. The problem we are dealing with is that we may have embeddings or vectors to represent individual concepts, but we also want to encode position, and we want to do it in such a way that it is immune to absolute position, and what it actually captures is relative position. Okay, so in this white-spaced example, if you look at the tokens the and dog, you see that in both sequences they are adjacent to each other. The is followed immediately by dog. That is what we want to capture. Okay? And this is again something that's going to be a feature of the EXD. It so happens that before I say that, we want q minus p is equal to 1. That is, we want the index of q of dog, which is q, minus the index of the, which is p, to be equal to 1. And it so happens, if positional encoding is doing its job, we want the dot product between these two vectors. I've written tokens here, but we'll see, what I mean is vectors that represent the tokens, to be the same, whether it is in positions 8 and 9, like here, or positions 0 and 1, like here. Okay, and this is because the dot product is the vector operation that drives attention. Okay, so we'll come to that later actually. So this is going to be something, we'll just assume that for now. It's kind of like looking at a piece of an engine and we see that a pipe comes out of here and attaches to some other part. We'll worry about what it means later. We'll just assume that, okay, we want the dot product to be the same. Okay, here's what it looks like mathematically. You want the dot product between the and dog in position 0 and 1 to be the same as the dot product between the and dog, positionally encoded. That's what this R means for 8 and 9. Okay, so more generally, basically what we're saying is, R of P is a rotational transformation of the vector A, which is dependent on the index P, and this is the rotation dependent on the index Q. So the rotated vectors A and B, depending on their P and Q, should only be a function of a, b, and q minus p, not the absolute values of q and p. Okay, I think that's fairly simple. Okay. Okay, this is called translation invariance, and it feels fairly obvious, right? Like if you want to encode position, we should do it in a translationally invariant manner. Cool. It so happens that among the family of transformations that satisfy this property of the dot product being the same, rotation is a very natural choice. Okay. And it has another benefit, which is it preserves vector norms, which simply means that the size of the vector doesn't change, right? You can see that intuitively. If I rotate a vector, the length of the vector doesn't change, just where it's pointing changes. So it feels like we're not adding some sort of new feature to things. We're just kind of like slightly rotating a vector and not rotating it and changing its distance at the same time. Okay, so this is why rotation was chosen as a means for encoding this extra bit of information on top of the static embedding vector for any given token. Now, I think we are going to start getting into linear algebra in the future, so it's really worth slowly introducing it. Some of these things, and I think I like to sort of get a picture of something at a high level and then slowly dig in, instead of kind of fully getting the foundation and then working upwards towards it. So some of these things you just kind of assume, and they'll make sense as we keep working with these things. And we'll do some further episodes specifically for linear algebra, just to strengthen our concepts. But for now, let's get a mathematical sense for how rotation works with vectors and matrices. Okay? Now, we know that vectors live in a 2048 dimensional space, but for simplicity, let's just imagine that we just have a two-dimensional space. And let's assume that the vector A is just 1, 0. Okay? So if you look at this space, this is a two-dimensional space. This is what we're talking about. We're talking about this position, right? 1, 0. That's A. And the way you write a 2D rotation matrix that rotates any given vector by theta degrees is this. You create a 2 by 2 matrix, cosine theta, sine theta, minus sine theta, cosine theta. This is a rotation matrix which will rotate this vector by this angle theta. Okay, all you have to do is multiply them together. So this matrix times A will give you the new matrix, will give you the new vector, the rotated vector. And it so happens for this simple 1, 0, right? And here, I'm going to assume that you remember some of this math from high school. If not, it's easy enough to get a quick refresher somewhere on the internet. So I encourage you to do that. But you can see that you get cosine theta and sine theta because the way you multiply this is cosine theta times 1 is equal to cosine theta minus sine theta times 0, which is 0. So you just end up with cosine theta. And sine theta times 1 plus cosine theta times 0 is just equal to sine theta. So r theta A, rotating A by theta, is just equal to a vector which is cosine theta by sine theta. So let's calculate this at specific angles. Okay, guys, so let's assume theta is 0. You're rotating it by 0. We're just confirming that we get the same answer, right? Cosine of 0 is equal to 1. So that's 1 on top, and sine of 0 is equal to 0. So 0 below. So you just reproduce the same vector. Okay. Let's rotate it by pi by 2. That's 90 degrees. So cosine theta by pi by 2 is equal to 0. Sine of 90 is equal to 1. So rotating by 90 degrees gives us 0, 1, right? 0 on the x-axis, 1 on the y-axis. Let's see, does that make sense? Rotating by 90 degrees counterclockwise. Yep, Oh, I should have mentioned that's the rotation matrix for counterclockwise rotation, right? So this is a counterclockwise rotation. So, yep, checks out. If you rotate 1, 0 by 90 degrees, you get 0, 1. All right. What happens if you rotate it by 180 degrees? You get -1, 0. Okay, you can do it. So cos of pi is equal to -1, sine of pi is equal to 0. So you get -1, 1. And finally, if you rotate it by 360 degrees, you come back to, sorry, there's one more step, which is, I guess, 270 degrees. 180 plus 90 is 270, yeah. That is 3 pi by 2. Then cosine of 3 pi by 2 is equal to 0. Sine of 3 pi by 2 is equal to -1. So you get 0 and -1. That's x is equal to 0. Y is equal to -1. You end up here. And finally, 2 pi. That's a full rotation. You return to your same position. Cool? This is how rotation works. You have a matrix. In this case, it's a two-dimensional matrix. You just multiply it with your vector and you get the rotated vector, which is also a vector, right? So 2 by 2 matrix multiplied with a 2 by 1 vector gives you a 2 by 1 vector. Okay, let's quickly show that this operation of rotation, right? And the reason we got this is just to sort of give you a feel for things, okay? And this is, okay, I'll admit this is just the way I learn. I need it to be concretized. I need it to be sort of something that I feel, as well as, you know, I can just follow the operations. Apart from following the operations, there's a bunch of math. It always helps me to sort of feel my way through these things. That's why I'm kind of going through this pedantic process. So what we want to do is just verify that, hey, if we do this, is the dot product maintained, right? So suppose I get two vectors here for this sentence. We have the and cat in two different parts of the sentence, of the same sentence, right? Here it's got the positions 1 and 2. And here the positions 7 and 8. And the relationship between each other, right, the way cat is related to the, is the same. So when we get to attention, when we do the dot product for the positionally embedded cat and the positionally embedded the here, and the positionally embedded the and the positionally embedded cat here, which are different vectors entirely, right? Their relationship should still be the same, right? We want the relationship to be maintained. So we should rotate them in such a way that the dot product between these two things doesn't change. That's what we're doing. Okay? And all of this will make a lot more sense when we hit the transformer next and we start doing attention heads. But we're going in order. It's fine. Meaning will slowly come as we proceed, as we take the engine apart. Okay, so let's just assume that the is represented by 1, 0 and cat is represented by 0, 1. Okay, and let's assume that for rotational embedding we just rotate by 90 degrees. Okay? Just for clean arithmetic. And what we're going to show is that, so we're going to, okay, well, there's one small point I need to mention. It's 90 degrees per position step. What that means is we'll rotate the by 90 degrees because its positions, its index is 1. Okay? And we'll rotate cat by 180 degrees, that is 290-degree steps, because its position is 2. So you can guess how many times are we going to rotate this the? We're going to rotate it 7 times 90 degrees. And this cat, we're going to rotate 8 times 90 degrees. Okay, that's what we're doing. So we already have their vectors, their individual vectors. We don't need to compute those. Those are statically determined in the beginning, right? If you remember the previous episodes. And now we want to add some information to them by rotating them. Okay? And the rule is rotate it by 90 degrees for its index. Okay? So if it's at index 2, then rotate it by 90 and 90, 180. If it's at index 7, then rotate by 90, 90, 90, 90, 90, 7 times. Okay? And if it is cat, rotate it 8 times. Cool? I hope that's clear. We have the individual vectors, and to encode their position, we rotate it by 90 degrees times the index. Okay. So let's get the first set of rotated vectors. And the goal is to show that the rotationally embedded vectors for this pair, if we take the dot product between them, we'll get the same answer as taking the dot product between the rotationally embedded vectors for this the and this cat. That's what we're trying to show. Okay, let's just show that this is true for 1, 0 and 0, 1, and then we'll just assume that therefore it's true for everything else and not actually do a proof. Okay, because we're slowly moving downwards. Okay, so theta for 1 is just equal to 1 times pi by 2, that's 90 degrees, and theta for 2, for the position 2, is 2 times pi by 2 is equal to 180 degrees, right? And that gives us 0, 1 for the rotated, right? And you remember we're rotating 1, 0 by 90 degrees, so that's 1, 0 by 90 degrees becomes 0, 1. Yes, makes sense. And B, which is equal to 0, 1 already, is going to be rotated 180 degrees, which we know is just a reflection to the x-axis, right? And so it's going to become 0, minus 1. And now we're going to take the dot product of these two vectors, and you get the answer minus 1. Okay? So the dot product between the first time the and cat appear, this first instance of the and first instance of cat, is minus 1. Now what we need to verify is that the dot product of the positionally rotated this positionally rotated the and this positionally rotated cat is also going to be minus 1. Let's see if that's true. Okay? So let's compute the second occurrence. That's the position 7. Okay? So 7 times pi by 2. Okay? We just end up with 270 degrees. Okay? And 8 times pi by 2, we end up with 4 pi, which is just like 2 full rotations, right? Think about it, this is 3 full rotations and then a bit. This is 2 full rotations. Okay? So, here we are. 270 degrees and 0. And for 270 degrees, you get cosine 270 is equal to 0, sine of 270 is equal to minus 1. Okay? So the rotation matrix is this. So for the 0 degrees, you get this. So now this is how you rotate the first for the 270 degree vector, right, which is the first and for cat, which is in position 8, this is the rotation matrix. Okay, now when you apply them, you get 0 and minus 1, and you get 0 and 1, and if you take the dot product between these two vectors, you get minus 1 again. Okay, I encourage you guys to actually open up the article, I'll link it below, and just go through it step by step with a piece of paper and see that it checks out. But the idea is basically, you see now that the dot product does not depend on the position. It only depends on the relative position, on Q minus P. You will always get the same answer. Okay? And just for comparison, for a different offset, if Q minus P is equal to 2, then you always get 0 as the answer. This is excellent for our next step in the series when we hit attention heads. We have found a way of encoding position such that it does not change depending on absolute position, but only on the relative position of words. Okay, that's the whole motivation for mRoPE. Great. Okay. Now, this was a toy example, and as I promised in this video, we'll actually understand just step by step. We may not understand why, but we will understand how this thing is done in Qwen 3.6. Okay, in the EXD, the why comes later. We start with the how, and the why slowly dawns on us as we put the whole engine apart and understand what each part does. So in the toy example, we use 90 degrees as our frequency, and we used a single 2D vector to represent vectors, but that's obviously not what we do, right? So let's break it down. This is how Qwen actually does it. Okay. First of all, Qwen exists in a 2048 dimensional real space. Okay, so the vector is inside this crazy multidimensional space. Okay, and we don't just rotate the one vector entirely. Okay, so we don't rotate this vector, which is in all these dimensions, in just one way. What we instead do is we split it into 256 dimensional subspaces. Okay, so 2048 divided by 256 is equal to 8. So we split the 2048 dimensions into dimensional space into 8 subspaces. Now, very quickly, just for intuition, okay, imagine you're outside on a sunny day and you're holding a pole at an angle to the ground, right? The bottom is resting on the ground and you're holding it at an angle. Imagine that's your vector, okay? And this is a vector in 3-dimensional space. The shadow of that pole on the ground, imagine it's noon or something like that, okay? The shadow of that pole is in a 2-dimensional space. So I'll just say that again. You're holding a pole in outside on a ground somewhere. It's noon. It's a sunny day. The pole itself is the vector in 3-dimensional space. Its shadow clearly is a vector in a 2-dimensional space, right? That's what a subspace is. The ground is a subspace of this 3-dimensional space. Okay? And this is a trick that we're going to do repeatedly. You know, like this is what Hinton said. You know, don't worry about multidimensional spaces. Just work with the intuition for what you already have. Luckily, we have 3, so we can imagine how we can think of a subspace in of 3-dimensional spaces as 2 dimensions, and we know how it works. Now it follows the same logic in multidimensional spaces as well. Okay, so this 256 dimensional space is kind of a shadow of the 2048 dimensional space in 256 dimensions, just as the shadow of the pole is a 2-dimensional vector, which is the a shadow of a 3-dimensional actual vector. Okay, you can't visualize this in your head. Just accept it. Just say, yes, this is, so imagine that the pole is 2048 dimensions and the shadow of the pole is the 256 dimensional subspace. Now you can imagine that the same pole, there's a wall next to you and you can shine a light, let's say from the right, and it casts a different shadow on the wall. That's a different subspace, right? You can, if you have X, Y, and Z, the first shadow was the XY plane and it was the XY subspace. And if you look at the what you're casting on the on the wall that is kind of like your XZ subspace, right? So, assuming that it's coming from one direction, right? So this is how you can have multiple different subspaces for a given vector. So each of these kind of are like the shadows, and if you think about it, all the shadows together add up to reconstruct the actual vector, right? So we're just splitting the dimensions up into these subspaces. Okay, I think I've belabored this point enough. What we'll do is we'll actually now within this. So we have taken this 2048 dimensional space, we have split it into 8 subspaces, each of which themselves have got 256 dimensions each. And within each of these, we only rotate 64 of the 256 dimensions. So we don't even rotate all the dimensions. We just rotate it in 64 of them, right? Now remember, this does mean that the vector is rotating. It's just that it's not rotating in those dimensions. Kind of like imagine you have the pole and you just rotate it. You don't change its angle relative to you standing up, right? You just kind of rotate it along the ground. What you're doing is you're rotating it over the x and y plane, but you're not rotating it relative to z, right? So similar to this, when you rotate 64 dimensions, it's not as if you're not rotating the actual vector, you are. It's just that those numbers don't change, okay? All right. Now to make things even more nuanced, we will not rotate all 64 of those dimensions the same amount. We'll split them into 32 frequency pairs, okay? So let's go back. You have a 2048 dimensional space. We split them up into 8 256 dimensional subspaces. Within each subspace, we take 64 out for rotation, leave the rest as they are. And those 64 we split into 32 pairs. So dimension 0 and dimension 1 are a pair. Dimension 2 and dimension 3 are a pair. So on and so forth until, 62 and 63, because we started at 0, right? And each of these pairs now is kind of like our toy 2D vector, okay? Here's the rule. Remember, previously our rule was 90 degrees per, where is that? Yes, 90 degrees per position step, right? So we had a rule that some number of degrees per position index, right? What we do here is we don't have the same amount of angle rotation for each position, for each frequency pair. What we do is this pair, D0 and dimension 0 and dimension 1, they rotate a certain amount per index. This pair rotates a little bit less. The next one even less. The next one even less, until the last one barely rotates at all. Okay? So it goes from fast to slow. So we do a different frequency of rotation for each pair of dimensions, for each of these 32 pairs. And the formula for it is this complicated formula where basically you have omega is equal to 1 by, this is a million, to the power of 2i divided by 64, where I is the index. Okay, so even the fast rotation is an extremely small number, as you can see clearly. And you basically get 32 such rotations. Okay, so if you set I is equal to 0, then you get a certain amount of rotation here. If you get I is equal to 1, you get a certain amount of rotation here. If you get I is equal to 2, then next. And finally, this last pair of dimensions has 2 times 31, so that's 62 divided by 64. Okay? So it turns out that pair 0 completes a full rotation every 2 by pi positions. okay? But pair 31 barely rotates, okay? It takes 10 to the power of, it takes thousands of positions to rotate. Okay, so this is called a frequency ladder. So what you're doing is you're kind of capturing positional relationship at every scale. Some of those things are very responsive to position and the others are actually not so responsive. So this is in order to capture relationships between words which are very close to each other, which would be captured by, the earlier dimensions in this 64 pairs, as well as words which are far apart in an input sequence, right? Like imagine two words which are in some corpus of text that you've entered as an input sequence. They're separated by a great distance. So let's say there's hundreds of index points between them, right? Those relationships are captured better by the dimensions which move slowly. Okay, because the first one would have just cycled round and round across the around the origin. So it doesn't really capture that information, but the later dimension is captured. Okay. That's actually it, guys. There is another step which we're going to skip. Okay, Quen 3.6 is multimodal. Should have thought about that before jumping into this series, but we're actually going to skip this. We're now going to talk about multimodality. We're instead going to just recap this one more time, just so we understand how mRoPE works, and then we're going to do it. We're going to pull the toolbox out, take the wrenches out, and do it on the real model. Okay? So here we go. Our goal is to rotate the static embeddings, the input embeddings of vectors, a tiny bit to represent their relative position with all of the tokens inside the input sequence. We want to do it in such a way that we can capture far relations as well as close relations. To do that, we take the 2048 dimensions of the input embeddings. We split them into 8 subspaces. Within each subspace, okay, it's called a pseudo head. Ignore that. Within each subspace, only 64 of the 256 dimensions rotate. Don't think of this as the vector splitting. It's the vector rotating, but it's rotating only in 64 of the 256 dimensions. Okay? And those 64 are grouped into pairs, so you get 32 pairs. And we rotate the pairs at different amounts. The early pairs are very responsive to position. So, they rotate quickly. And the late pairs are more sensitive to far apart relationships. Okay, so they rotate only a tiny amount. And that's it. Okay, so let's do this. Let me now pull up this. This Jupyter notebook is available for download, obviously, from the article. You can just click this and download it, right? You can download it from Hugging Face. Don't open it in Colab because you'll have to load the tokenizer. It's not going to work in Colab unless you, I guess, pay for it or something. It's just complicated. Download it and run it on your system. Let's just do this just to get a sense of all the things we talked about. Okay, let's get pairs of tokens which should have the same relationship. Let us load their real embeddings. Let us rotate them using our logic. Then let's show that it's translationally invariant. Okay, so we'll just skip over to the Jupyter notebook. What we're doing is we're loading the embedding matrix. Let me just get some setup cells going. This is not something we need to really look at, except maybe we can look at the mRoPE configuration here. These are the 256. That's the size of the subspace that we want. So we'll get 8 subheads by dividing these two numbers, right? So number of heads is equal to hidden size divided by the head dimensions. This is our rope theta. This is the 10 million. It wasn't a million, it was 10 million. And these are the frequency pairs, right? So that's what you remember, and we'll use all these to in the math that we already went over. So let's get the vector for dog. Okay, so we've also downloaded the tokenizer, by the way. TOK is the tokenizer, right? And let's download it. Okay. Of course, it's a 2048 dimensional vector, so we can't see all of it. But this is what the vectors look like. I just kind of like to look at all these things. See, it has 2048 dimensions, right? This is its token ID. Okay. Let's pull out the heads. Let's break it into the subspaces. That's what we're doing here, right? So after reshape, we've basically broken this into, you can think of this as 8 rows of 256 columns, right? Or the other way around, whichever you prefer. And so each of these is called a head, right? And these are the first six dimensions of the head. Okay, so you can think of these as individual vectors, each of 256 dimensions. Okay, and remember, we will rotate within each of those. That was the next step, right? So this is how we do it. So we're splitting the rotary part, which is the first 64 dimensions. If you guys remember your pandas notations, that's how, or your vector notations, I should say, numpy vector notations. This is all the rows, but up to rotary dim, which was 64, right? Dimensions. And the free part is all of the rows from 64 onwards. Cool? They stay frozen. So the free part doesn't get rotated. We're just confirming that this is what we have. And we can do pairs, right? We can take these 64 dimensions and group them into pairs. Okay. So step 4 is the frequency ladder. This was the formula. It's 10 million, right? This formula over here. That's what we're implementing. We've already gone over the formula. You can please verify this, the code yourselves. And what we're showing here is how much of a position difference it takes to rotate the dimension entirely, right? So this rotates, this completes a full rotation every 6.3 positions. That's pair 0. Okay. Pair 10, here the pair we're talking about is a dimension, remember that. It takes 967 positions or index number for it to complete a full rotation. And pair 31 takes this insane 3.8 to the power of 7. Okay. So that just shows you the way in which we're kind of, imagine like I don't know, a fan of chopsticks or something, and they're each moving in different amount. Some move a lot, the others move very little. Like a fan of cards or something like that. Okay, so we have all the pieces. Let's rotate to real embedding. Okay, do some Python stuff. Let's apply, we have an apply rope function, right? Which I'm not going to go through. Okay, let's run it. So this is at position 0 and this is at position 5, and you can see it has been rotated. Okay, and these are the dimensions that do rotate. Remember, this is head 0, and you can see that in the position free dimensions they haven't changed. Okay, we have taken the vector for dog. Okay, we have applied this thing that we have described, and we have rotated only some of the dimensions and left the others unchanged. Okay, now what we want to show is that if we do this for the cat and the dog, right? The dot product between the and the cat here, which will have different values because they are rotated based on their position 1 and 2. And the dot product between the cat and the dog here will be the same. Okay? Through this complex rotation, kind of rotation that we've done. Okay? That is what this does. And here you see. Okay? So the cat here has the positions 1 and 2. That is this. And their dot product is this value for this number. Okay, we're just taking a dot product of the actual vectors that Quen gives us. And here we have taken the vectors for 7 and 8 and their dot product, and we get exactly the same number. And just for contrast, we show that the and dog is a totally different number. Okay? Okay. I think this is a great time to stop because we have covered a lot. We talked about why we need to add positional embeddings to the static input embeddings, which don't encode relative position inside the input sequence. We talked about a toy way of doing it with just like the two-dimensional vector, just to get a feel for it, just to get a handle on what we're doing with these vectors. We're taking a vector, we're rotating it, and then we're taking two of these vectors who are slightly differently rotated, and then taking a dot product between them, seeing the value, and confirming that if the same two vectors, if they're the same relative position later on in the sequence, and they're rotated slightly differently, even then, when you take the dot product between them, if the rotational algorithm is good, you will get the same result. That is basically what we've shown with actual Quen embeddings. Okay, that was the point of this exercise. Great, now you know. Next episode, I think we are ready to either talk about multimodality a little bit, or we'll just skip that and jump right into the transformer and attention to understand why we did all this and why the dot product being the same is so important. See you guys then.